Welcome back to the another session in design and analysis of algorithms and unit 1 topic 6 master's theorem. The master theorem is a fundamental tool in analysis of algorithms and it provides a straightforward way to analyze the time complexity of an algorithm. It follows a specific recursive form used to calculate the time complexity of recurrence relations, divide and conquer algorithms. And that specific recurrence relation is what? T of n is equal to A into T of n by B plus f of n, where n is the size of input and A is equal to number of subproblems in the recursion and n by B is equal to size of each subproblem. F of n is equal to cost of the work done outside the recursive call, which includes the cost of dividing the problem and cost of merging the solution. And the very most important point is what? Here A is greater than or equals to 1 as it is having number of subproblems. And B is greater 1. Both are constants, whereas f of n is what? Asymptotic bound. An asymptotically positive function means that for a sufficiently large value of n, we have f of n greater than 0. If a greater than 1 and b greater than 1 are constants and f of n is an asymptotically positive function, then the time complexity of a recurrence relation is given by T of n is equal to A into T of n by B plus f of n, where T of n is equal to, if the f of n is order of n power log b a minus epsilon, then theta n power log a b. If f of n is equal to theta of n power log a b, then theta of n power log a b log n. If f of n is equal to omega of n power log a b plus epsilon and a f of n by b is always less than from some constant into f of n for all large n values, then that theta is equal to theta of f of n, where epsilon is always greater than 0 and constant is less than 1. This is what the recurrence relation, the specific form of recurrence relation. Now there are three different cases. Now we'll see three different cases with the example. The first different case is what? F of n is equal to order of n power log b a minus epsilon. The first case 1 is equal to, if f of n is order of n power log b a minus epsilon for some constant where epsilon is greater than 0, then it follows the time complexity T of n is equal to theta of n power log a b. Now we'll take some example. The example is what? T of n is equal to 8 T of n by 2 plus 1000 n square. Now we were discussed in the previous slide that the recursive form of master theorem will be very different than the previous recurrence relations, and this is what a specific form where master theorem can be applied. And here n is what? The size of input. This is what the size of input, and a is what? Number of subproblems in the recursion, and this n by b is size of each subproblem, and f of n is what? The cost of the work done outside the recursive call, which includes the cost of dividing the problem and cost of merging the solution. Now compare this T of n is equal to 8 into T of n by 2 plus 1000 n square with T of n is equal to a into t of n by b plus f of n, where a is always greater than or equal to 1 and b is greater than 1. Now find out the values of each. A value is 8. When you compare these two, you will get the value. A is equal to 8 and b is equal to 2 and f of n is equal to 1000 n square and log ab is equal to log 2 base 2 8, which is this 8 can be written as 2 cube. Log 2 base 2 is 1 and the answer is 3. Now put all the values in f of n is equal to order of n power log b a minus epsilon. Now f of n is what? 1000 n square. 1000 n square is equal to order of n cube. Log ab value is what? Log ab value is 3. N cube minus epsilon. Now if we choose epsilon value is equal to 1, then we get function f of n is equal to 1000 n square, where big O of n cube minus 1, where it is big O of n square. So the time complexity T of n is equal to big O of n power log ab. Log ab value is 3, that is of big order of n cube. So that is what the first case. Now we'll see even case 2 also. The case 2 is what? If it is true for some constant k is greater than or equal to 0, that f of n is equal to theta of n power log ab and log k n, then it follows that t of n is equal to theta of n power log ab log k plus 1 of n. Now we'll see some example to satisfy the second case. Now assume that t of n is equal to 2t of n by 2 plus 10 n. Now again we'll compare the function. Now compare t of n is equal to 2t n by 2 plus 10 n with the standard master theorem. T of n is equal to a into t of n by b plus f of n, where a greater than or equal to 1 and b greater 1. Put all the values in f of n is equal to theta of n power log ab log k n. Now we will get 10 n is equal to theta of n power 1, where theta of n, and which is true. Therefore t of n is equal to theta of n power log ab into log k plus 1 base n. So finally theta of n log n. So this is what case 2. Even we have a case 3. That case 3 is what? If it is true that f of n is equal to omega of n power log b power a power plus epsilon. For some constant epsilon is greater than 0, and it is also true that f of n by b less than or equal to c f of n for some constant c less than 1. For large value of n, then t of n is equal to theta of f of n. So this is what case 3. Now we'll take some example to solve the recurrence relation, where it is t of n is equal to 2 into t of n by 2 plus n square. Now a value is 2 and f of n value is n square, b value is 2. Right, now we'll compare with the standard formula. So compare the given problem with T of n is equal to a into T of n by b plus f of n with a greater than or 1 and b greater 1. So where a is equal to 2, b is equal to 2, f of n is equal to n square. And what is the value of log b base a, which is log ab values are log 2 base 2 and which is 1. Now put all the values in f of n is equal to omega of n power log b base b a plus epsilon. Assume that it is equation number 1. Now if we insert all the value of equation 1, we will get f of n value is n square is equal to omega of n power 1 plus epsilon. Put epsilon is equal to 1. Then the equality will hold. N square is equal to omega of n plus 1 where it is omega of n square. Now we will also check the second condition, where the second condition is what? 2 into n by 2 whole square less than or equal to cn square if and only if 1 by 2 n square less than or equal to cn square. And if we will choose c is equal to 1 by 2, it is true 1 by 2 n square less than or equal to 1 by 2 n square for all n greater than or equals to 1. So it follows t power n is equal to t of n is equal to theta of f of n. So finally t of n is equal to theta of n square, because f of n value is n square. So this is what the case 3 in Master's theorem. Thank you all.